You open the AWS console and click Create Load Balancer. 3 options: ALB, NLB, Gateway. You pick one, traffic flows, and it just works. But what actually happens under the hood? Behind that one click, there is a custom silicon chip processing packets, a fleet of thousands of invisible servers, a network virtualization platform that powers half of AWS. And most engineers have never heard of them. What AWS actually uses behind its load balancers, Layer 4, Layer 7, and the technologies that make them possible. The complete engineering deep dive. Here is our roadmap. We will start with the old world of classic load balancers, then explore the Nitro chip that powers modern ALBs. We will deep dive into how ALB processes Layer 7 traffic, uncover Hyperplane, the hidden giant, dissect NLB at Layer 4, examine Gateway Load Balancer, compare L4 versus L7, and see real-world architecture patterns. Let's begin. To understand modern AWS load balancers, we need to go back to the physical world. Think of an old-school data center. You had a big metal box, the load balancer, sitting in a rack. It had special chips called ASICs that processed packets at wire speed. All traffic hit one virtual IP, and the box spread it across servers behind it. But physical boxes had limits. Scaling meant buying bigger hardware. Redundancy required an active standby pair, synchronizing TCP sessions across 2 devices. If the primary failed, the standby took over. It was expensive, brittle, and couldn't scale past one rack. AWS rebuilt this as a service in 2009, the classic load balancer. Think of it like moving from owning a delivery truck to using a shipping service. Under the hood, AWS ran EC2 instances in a hidden service VPC. They attached special cross-VPC network interfaces into your VPC. DNS resolved your load balancer hostname to these instance IPs, one per availability zone. Here's where it got messy. When traffic spiked, AWS added more instances behind the DNS name. You could literally see additional A records appearing. Partners like Palo Alto had to poll the DNS every second to discover new nodes. For big events, you had to call AWS support and ask them to pre-warm your load balancer. That is like calling the shipping company a week before Black Friday and saying, "Please add more trucks." Now let's meet the technology that changed everything, the AWS Nitro System. Before Nitro, network processing ran in software on the host CPU. Think of it like a restaurant where the chef also takes orders, washes dishes, and handles the cash register. Nitro moved all that work off the CPU and onto a dedicated hardware card. The Nitro system has 3 components. First, the Nitro card, a custom network interface card with its own processor that handles all packet processing at hardware speed. Second, a minimal KVM hypervisor, just enough firmware to run virtual machines. Third, the Nitro security chip, which validates the hypervisor firmware has not been tampered with. The numbers tell the story. In 2013, instances could push 10 gigabits per second. By 2021, 50 gigabits. Today, a single C8GN instance with Nitro can handle 400 gigabits per second per network card. Stack multiple cards, and you reach 12.8 terabits per second per instance. That is more bandwidth than some countries have. Nitro version 3 and above also encrypts all traffic by default, end-to-end, in transit, automatically. No code changes needed. AWS recently added VPC encryption controls that enforce Nitro-based encryption account-wide. Every ALB and NLB automatically upgrades to newer Nitro families to support this. Now let's open the hood on the application load balancer. ALB is a Layer 7 proxy. Think of it like a smart receptionist who reads your invitation before deciding which room to send you to. It terminates your HTTP connection, inspects headers, cookies, and paths, then forwards the request to the right target. Under the hood, ALB runs on Nitro-powered EC2 instances inside a hidden AWS service VPC. Similar architecture to the classic load balancer, but supercharged by Nitro hardware. When you enable an availability zone, AWS creates a dedicated load balancer node in that zone. Each node acts as a full HTTP proxy. With cross-zone load balancing enabled, every node can route traffic to targets in any AZ, not just its own. ALB scales aggressively. When traffic spikes, AWS scales up the proxy instances to bigger types and scales out by adding more nodes. Unlike the classic load balancer, this happens invisibly. The scaling system intentionally over-provisions to survive an entire AZ failure. It scales down conservatively, slowly removing capacity to avoid thrashing. ALB offers 3 routing algorithms. Round-robin distributes requests evenly. Least outstanding requests sends traffic to whichever target is least busy. And the new target optimizer, designed for AI workloads, limits each target to a single concurrent task using an agent running on the instance. On top of that, ALB integrates WAF for DDoS protection, Cognito for authentication offload, and supports SSL, TLS, and mutual TLS for end-to-end security. Here is the biggest secret in AWS networking. It is called Hyperplane, and it powers nearly everything. Think of it like the underground plumbing of a city, invisible, essential, carrying water to every building. Hyperplane is a network function virtualization platform. Here is the magic. In the old world, each load balancer instance had its own IP. When you scaled, new IPs appeared. Hyperplane flips this. It gives you exactly one IP address per availability zone, one ENI, one interface. Behind that single IP sits a fleet of thousands of EC2 instances. AWS can add or remove instances without you ever noticing. No more DNS polling. No more pre-warming phone calls. For reliability, Hyperplane uses a cell-based architecture. Think of apartment buildings in a city. Each cell handles a portion of traffic independently. A failure in one cell cannot cascade to others. Routing between cells uses a cryptographic hash function to distribute requests evenly. Hyperplane is not just for load balancers. It powers NAT gateways, private link, transit gateway, Lambda networking, VPC endpoints, and more. Every new networking service AWS builds uses Hyperplane underneath. When you create a NAT gateway or establish a private link connection, you are using Hyperplane without knowing it. The network load balancer is the crown jewel of Hyperplane. Unlike ALB, which uses proxy instances, NLB works at layer 4. Think of it like a highway interchange. It doesn't read your mail, it just routes your car to the right exit based on the license plate. Ultra fast, because it never opens the packet. NLB uses a 5-tuple hash algorithm to pick a target. 5 inputs go into a mathematical function: the protocol, source IP, source port, destination IP, and destination port. For TCP, it adds the sequence number, making it a 6-tuple. The output is a number that maps to one of your targets. Same 5-tuple always hits the same server. NLB maintains lightweight connection tracking, not full stateful inspection. It tracks active TCP connections to enforce idle timeouts. 350 seconds for TCP, 120 for UDP. Packets that don't match an active connection, like stray ACKs or FINs, get a TCP reset. This gives you some protection against ACK floods without the overhead of deep packet inspection. One killer feature: NLB powers AWS Private Link. Instead of routing traffic over the internet or through a transit gateway, Private Link creates a direct tunnel using the NLB and Hyperplane. Traffic stays on the AWS backbone, never touches the public internet, and uses the local subnet IP, as if the service lived next door. The newest NLB feature is QUIC pass-through. QUIC is the protocol behind HTTP/3, built for mobile devices that change networks constantly. NLB does not terminate the QUIC session. Instead, it reads a special field called the Destination Connection ID to maintain stickiness. Even when a phone switches from Wi-Fi to cellular, the connection stays alive on the same backend server. The third load balancer is Gateway Load Balancer. Think of it like an invisible security checkpoint on a highway. Every car passes through without knowing it is being inspected. GWLB sits transparently in the traffic path, sending every packet through a fleet of security appliances like firewalls from Palo Alto or Checkpoint. Here is how GWLB achieves transparency. It uses Geneve encapsulation, wrapping the original packet inside a new one, like putting a letter inside a second envelope. The outer envelope goes to the firewall. The firewall unwraps it, inspects the original letter, rewraps it, and sends it back. The original source, IP, and destination are perfectly preserved. The end server never knows its traffic was inspected. Here is an important detail most people miss. A GWLB deployment uses 2 Hyperplane fleets. The first fleet runs the gateway load balancer endpoints in your VPCs. The second fleet runs the actual gateway load balancer in the security VPC. Traffic passes through both fleets to reach the firewall appliances. GWLB guarantees flow stickiness. Both directions of a connection always hit the same firewall. This is critical because stateful firewalls need to see both request and response to make security decisions. Let's put it all side by side. Layer 4 load balancing, that is NLB, works at the transport layer. It sees IP addresses and ports, but never reads the HTTP content. It is like a mail sorter who reads the address on the envelope but never opens it. Layer 7, that is ALB, opens every envelope, reads the letter, and decides where to deliver it based on the content. This means NLB is faster. It processes millions of connections per second with sub-millisecond latency. ALB adds a few milliseconds because it terminates the connection and proxies it. But ALB gives you superpowers: path-based routing, host-based routing, WEF integration, authentication offload, and HTTP header inspection. Choose NLB when you need raw speed. Choose ALB when you need smart routing. Under the hood, the technology differs too. YLB runs on Nitro-powered proxy instances, similar to the classic load balancer, but with hardware acceleration. NLB runs on Hyperplane, the distributed network function virtualization platform. YLB scales by adding bigger instances. NLB scales by adding invisible fleet capacity behind a fixed IP. Let's build a real architecture. A 3-tier web application. At the front door, YLB handles HTTP traffic, applies WAF rules, and routes by URL path. /API goes to your backend, /static goes to your CDN origin. Behind it, NLB connects your backend to a database VPC over private link. Secure, fast, private. No transit gateway needed. Now at security, Gateway Load Balancer sits at the VPC edge with ingress routing. Every packet entering from the internet passes through firewall appliances first. The database VPC gets its own GWLB endpoint, so even internal traffic is inspected. All 3 load balancer types working together, each in its sweet spot. For Kubernetes workloads, the AWS Load Balancer controller automates everything. YLB acts as the ingress controller for path-based routing to services. NLB with direct pod mode assigns pod IPs directly to the target group, skipping the Kubernetes service proxy entirely. This gives you the lowest possible latency for performance-critical pods. Here is the mental model. At the foundation, Nitro provides hardware-accelerated networking. Hyperplane virtualizes that into a scalable fleet behind fixed IPs. YLB sits on top of Nitro as Layer 7 HTTP proxies. NLB sits on Hyperplane as Layer 4 connection routing. And GWLB uses Hyperplane with Geneve encapsulation for transparent security inspection. The key insight: AWS didn't just build load balancers. They built 2 foundational platforms, Nitro and Hyperplane, and then composed different load balancers on top. That is why NLB, NAT Gateway, and Private Link all share the same superpowers: single IP, infinite scale, zero pre-warming. They are all Hyperplane. Next time you create a load balancer in AWS, remember, you are not just clicking a button. You are deploying custom silicon, a city of invisible servers, and decades of network engineering, all behind one API call. Thank you for watching. If this helped you understand what happens behind AWS load balancers, consider subscribing. See you in the next deep dive.